What I'd like to talk about now is the significance of the pump performance curve, which basically provides all the data that we need that documents the pump performance of flow, head, power, and efficiency. And we normally start off by showing that graphically by drawing a graph where we've got flow across the horizontal axis. We normally call that Q, and head at the vertical axis, which we normally call H. So those are the major parameters for a pump performance. And as flow increases, we see that head will vary. The standard HQ curve for a centrifugal pump looks basically like that for a fixed speed and a fixed impeller diameter. So as flow increases, the head drops. Okay? And we produce this information by actually type testing a pump. So this is not based on calculations, this is based on physical testing of the product. And we normally have various impeller diameters. This might be D1, that would be the maximum diameter, and we'll see other HQ curves that go down to provide down to D2, D3, D4. That's typical of the sort of performance curve you would see for a fixed speed and that might be a two-pole speed, which is 2,900 RPM, or it might be a four-pole speed, which is 1,450 RPM. So those are typical formats for a pump performance curve, okay? We would then, when we test that, calculate what the power required is for developing these various duty points. And we would have power curves that will look like this. And the important ones are the power at best efficiency point and the power at end of curve. And then we would have efficiency lines, which are like this. And this would be the best efficiency point or the design pump for that particular pump. So this would be BEP flow. And that's a very important point on the pump curve because that defines the preferred operating zone for the pump. Okay? So here we've got kilowatts, and here we've got efficiency. Let's say the premium efficiency might be 70%. This might be 65, 60, and 50. That's typical of the sort of parameters that you would have on a pump curve. So what's the significance of this information? This information, as I said, is for a fixed speed, but with varying impeller diameters. Down the bottom, we're going to have an NPSH curve, and this is NPSHR for the pump over the operating range, and that would normally be a disc shape like this and vary from 6 down to 0 meters. Typical NPSH range, okay? So all this information is provided in a published performance curve issued by the manufacturer. However, to examine the accuracy of this information, we need to understand how that data was collected. And as I said, this is done by physically testing a model of the pump. So if this is, let's say, a 150 by 125, 500, that would be a typical ISO pump. Suction, discharge, impeller diameter. We would take that product, we would put it onto a test bay, and we would produce a result. This pump would have to be tested to the test code, which is ISO 9906. And there are 3 grades of testing 49906, grade 1, which is a high grade, grade 2, which is a medium grade, and grade 3, which is a commercial grade. And that affects the acceptance tolerances of this data. A normal published curve given to you by a pump manufacturer would in fact be to grade 3. And the grade 3 tolerances for Q are plus minus 9%, and for H they are plus minus 7%. So that immediately gives you an idea as a pump user how accurate the information is in the pump performance curve. This is an international standard, so every pump manufacturer provides you exactly the same information if they test it to ISO 9906 grade 3. Okay? So you've got to understand that the published curve is going to be subject to tolerances for flow and head, which means that what you see on the curve may not be produced by the pump when you take it to site. Okay? There is another thing that we should understand, that when we look at this vertical line, that's the headline, what we're actually drawing here is energy provided to the pump. And that energy provided to the pump is in two forms. It's in potential energy as pressure, and it's in velocity energy as kinetic energy. Okay? So we've got two components in this line. One of them is easy to measure because we can put a pressure gauge on it. But the other one is more difficult to measure because it means that we must know the velocity in the suction and the velocity in the discharge. And if there is a difference in velocity, that is represented by the velocity head component of the pump calculation. So in fact, if you're just measuring pressure, what you will find is that the velocity head is 0 at 0 flow. But as the pump flow increases, the velocity head will also increase. And the actual pressure line is the difference between the velocity head line and the total energy line. So this is the pressure line that you measure on a gauge, and this is the manufacturer's estimate of total energy added to the fluid. Now, a lot of pump users don't understand that factor about the information that's provided in a pump performance curve. And that's because taking a pressure measurement is easy. You just stick a gauge on the suction and a gauge on the discharge, and you measure the differential. And that gives you the pressure differential that the pump can produce. It does not give you the velocity head component, which increases as flow increases. So through a pipe, let's say the pipe is 150 millimeter diameter, if you push 50 litres a second through it, you've got a particular velocity head. If you put a higher flow through it, you put 70 litres a second through it, you'll get a higher velocity head. And those factors are not shown on the pump performance curve. So if you're looking at a pump performance curve and matching it to a system curve, you have to be very careful about where your actual operating pressure will end up. So the message here is understand exactly what the performance curve is telling you. Understand what it does tell you and what it doesn't tell you, and the test standard which gives you the accuracy of the information that's contained in that document.